Hi, this is Dr. Justin Essery, and this is week 2 of Bayesian and nonparametric computational statistics. And this week we're going to talk about Bayesian inference, introduce you to the concept of Bayesian inference, and start to deal with some of the technicalities, but mostly deal with how it is we think about the relationship between evidence and theory or ideas, conclusions in the Bayesian framework. And as I've noted here, in political science, Bayesian inference encompasses many interrelated but distinct ideas, which is to say that Bayesian inference is not just a collection of tools, of statistical tools, but it's also an epistemological viewpoint about how evidence and conclusions are related. That is to say that the tools that Bayesian inference offers are grounded in some ways in a particular point of view. So are the frequentist tools that are more commonly taught, that you were probably introduced to in your previous classes. Often those tools are not necessarily taught with those epistemological conclusions up front. Nevertheless, they're there. And part of what we want to do today is talk about how those conclusions, the conclusions of so-called frequentist statistics, are different than the conclusions or foundational ideas of Bayesian statistics. And that's going to eventually lead us to down a different technical road. It's going to lead us to embrace different technical tools, which some of which are going to turn out to be very useful. Bayesian statistics also encompasses a mathematical argument about the logically correct beliefs one should hold given what you know prior to conducting a particular analysis, plus whatever information is contained in a data set. And to preview what this is getting at here, this is in essence a longhand way of stating Bayes' rule, or stating what Bayes' rule talks about, rather. Given what we know before we start a study and what we learn from a study, there is an expression, a mathematical relationship that tells us what we should believe after the study. This is one of the foundational ideas of Bayesian statistics, and it's less epistemologically laden, perhaps, than these previous ideas. Which is to say that I think many frequentists would accept Bayes' rule as being true. Nevertheless, these epistemological ideas inform how we use Bayes' rule to come to conclusions, that is to say, how we think about the relationship between evidence and conclusion. So even though frequentists probably accept that Bayes' rule is true, they may not agree with Bayesians about the particular uses to which Bayes' rule is going to be put. So as we go down the list here, you can see we're sort of moving toward regions of greater agreement, I guess you might say, which is to say less controversial issues. And down at the bottom here, Bayesian statistics can be thought of as just a set of technical and computational tools for doing things, which is to say an estimation procedure or a set of tricks and ideas that we can put to use to squeeze information out of a data set. And certainly plenty of frequentists accept that the technical and computational ideas on which Bayesian statistics is built are interesting and useful. In fact, one could use these tools, which we're going to mostly focus on in later lectures, but we'll hit on it a little bit in this lecture. You can use those tools without necessarily accepting the philosophy that comes along with Bayesian statistics. A frequentist, for example, might find Markov chain Monte Carlo sampling, which is something we'll talk about later, to be a useful way of estimating some parameter that they're interested in. That doesn't mean that, which is an MCMC is typically associated with Bayesian statistics, that doesn't mean that frequentist would necessarily accept a Bayesian viewpoint on the world, a Bayesian way of thinking about how evidence and conclusions are linked. So this third thing, the technical and computational aspects of Bayesian statistics, this is where a lot of the statistical and computational action is. I misspelled statistical there. And this is where we're going to spend a lot of the rest of the course, learning tools, techniques, tricks, computational algorithms, and the like. But before we get to that, we'll have plenty of time to deal with that. Today I want to talk about epistemology a little, and Bayes' rule in particular, and just give you a little sense of how Bayesians think about the world and how that comes out in some of their basic techniques. So that's what we'll be doing today. Let's go ahead and get started. So what's the difference between Bayesian thinking and frequentist thinking? This is just a brief introduction to the topic. There's nothing I'm going to say today, at least, and perhaps nothing that can be said in general, meaning, how do I put this? I'm not necessarily sure that Bayesianism and frequentism are developed enough, even in the practical statistical literature, to constitute a holistic epistemology or philosophy of science. But it is very fair to say that a lot of the discussions of Bayesianism and frequentism in that literature, in the statistical literature, have an epistemological flavor and make epistemological claims. And those claims are very different from one another and lead down different roads, both technically as a matter of estimation and philosophically or scientifically in terms of how they think of what evidence does and what it's used for and how we form conclusions based on evidence. So I want to talk a little bit about what these different ideas are, just to give you a sense of how Bayesians might think differently from frequentists. So frequentists presume or believe that there's a knowable state of the world that corresponds to some thing that we're going after, that we're estimating. And there are lots of ways this comes up in teaching and in research. But one very typical way it comes up is in the frequentist notion of bias, which is to say, look, we are going after an estimate of some quantity, right? Like, for example, a beta in an ordinary least squares regression model. And we're going to estimate that beta using a model and get a beta hat. And it's really important to a frequentist that beta hat be an unbiased measure of beta. In other words, that on average it yield correct estimates of beta. Now, the logic that underlies this is that there is a beta out there to be found, and we can find it if we have the right model, if we've specified the correct model. And a bad model gives us a bad estimate of beta, a biased estimate of beta, and we could do better if we simply had the right model. None of this makes any sense. None of that talk makes any sense if there is no beta. In other words, if you don't think of there being a real parameter out there in the world that you're trying to measure. Speaking of bias in the estimate of a fictitious non-existent quantity doesn't make a lot of sense. So if you're a frequentist, you think that there is of course, trivially, you think there's a world out there to be discovered, but that's not really what I'm talking about. What you think is that there is a structure to a data-generating process that your goal is to mirror or match. There's a DGP, a data-generating process running out there in the phenomenon that you're studying, and the goal of your model is to match that DGP as closely as possible and recover the appropriate parameters from the DGP. So if you run a linear model, that's because you think the world is either a linear model or at least can be approximated by a linear model closely enough to warrant that choice. So given that there's a real model running out there, you have uncertainty in your estimates, even if your model is a good one, a perfect one. And that uncertainty comes from the fact that the data generating process includes noise, which is just a way of saying that the world is not merely composed of signal, but also composed of noise. There's a lot of, I just sort of said the same thing twice. Even causal processes have things that are external to those processes that impinge on the relationship between an independent and dependent variable. There are sort of other modeling, other data generating processes that are operating in tandem with the one we're studying that can force their way into our DGP. And there may be irreducible randomness present. In fact, we know that there is irreducible randomness present in the world such that even when we know the data generating process, there's a limit to which we can understand the past and predict the future. In other words, some part of the DGP is unknowable from our perspective. It's just noise. Explaining it would be like trying to explain the static that used to appear on old analog television sets. There's just nothing there to explain. So there is a real DGP out there whose parameters we're trying to capture, but that DGP includes noise, which is unexplainable and which obscures our ability to see those parameters. And so as a frequentist, what you end up producing is probabilities that a particular estimate that you get occurred given a state of the world. That should not be Boise, that should be noise. Let's correct that. So what am I saying here? When you run a frequentist analysis, for example, when you run a maximum likelihood analysis, what are you doing? You are picking parameters so that the probability of the data given your chosen parameters is maximized. That's what a likelihood function is. It's a probability that it's a joint probability that this data set occurred given the parameters you've chosen. Maximum likelihood estimates maximize that quantity. So ML maximizes this. So that also implies that when you get things out of this estimate, they're really the probabilities you get out of these estimates are not necessarily about the parameters, they're really more about the data. So for example, we can estimate uncertainty around a beta hat, and we can represent that uncertainty in p-values, but a p-value is not a probability that beta is some particular value. That probability is instead the probability that we observed this particular beta hat given that the true beta is something equal to some quantity or less than some quantity or whatever. So for example, we might say, actually I should really correct this because the traditional p-value is not that beta is less than 0, but beta is equal to 0. We can say, look, there's noise in the world. So even if there's no relationship between x and y, sometimes because of that noise, we get samples that indicate that there is a relationship even when one's not there. Those relationships are then captured in beta hats. Fine. What's the probability that we would see a beta hat of this particular size, this particular beta hat, if it's the case that the true beta hat is 0? What's the probability that that would happen? A frequentist says, well, that is informative because, well, what we're trying to do is decide, well, I don't want to conclude that beta is not 0 if the world is pretty consistent with the idea that beta actually is 0. It sort of makes some sense, but you can already see where there's a string of logic going around that's kind of confusing and backwards from the way that we might ordinarily think about these problems. Nevertheless, this is what you get out of a frequentist analysis. What you get is function or probabilities that estimates occur, that data sets occur, or that estimates from those data sets occur given a state of the world. And then that's the information you have to draw on when you're coming to some kind of conclusion from a theoretical or scientific perspective. Bayesians, on the other hand, are interested not necessarily in mirroring a DGP, but in trying to establish a connection between beliefs and evidence. So you have beliefs about the world. Maybe they're true. Maybe they're not true. We don't really know that. What we're interested in is, are they consistent with what I see out there in the world? Are these beliefs things that would be supported or were coherent with the relationships that I observe in the world? If so, great. If not, let's change our beliefs. That's the Bayesian perspective. So the fundamental question they're asking is, given what I saw, given what I believed before this study, and then given what I saw in this study, what should I believe now? Now, this is the kind of thing you might ask even if your beliefs are known to be useful fictions. So, for example, I may know full well that neoclassical economics or that utility maximization, this is not something that this is not the way people's brains actually work, at least not for many choices that they make. But it's a useful fiction that we carry on because it simplifies the world in a helpful way. And I want to come to some beliefs about how that process is happening, what people are valuing when they make their choices. So I go into this knowing it's a fiction. I can come up with a Bayesian estimate of which beliefs about sort of how people juggle utilities in their head are most consistent with the evidence, even if I know that that whole framework is just a useful fiction, because I'm never arguing that the utility maximization is the DGP. I'm simply asking how consistent are certain viewpoints on utility maximization with what I've seen out in the world. And like frequentists, Bayesians believe in uncertainty in their estimates, and they believe that comes from noise in the data-generating process. But there are other sources of noise. For example, it may be the case that there are multiple states of the world, multiple models operating in the same time that are either exclusive or non-exclusive. And noise can come from the fact that we're only looking at one of them, or that we're looking at the only one, but we're looking in a kind of wrong way or something like that. And it may simply be that our evidence is incomplete. We have uncertainty about the world because we haven't looked at every possible realization of the DGP, and so we have ignorance that we need to quantify in some way. So you might have noticed that these things are connected in some way. Both of them are interested in looking at the connection between our ideas and the world. Both of them are interested in quantifying uncertainty. But Bayesians are not as, at least in the PR literature, meaning like the way they present themselves, I think it's fair to say that Bayesians are not as interested in capturing the true model. They're just interested in making sure that they're interested in maximizing the consistency between whatever their model is and the beliefs and the evidence that we have in hand. And furthermore, they're not interested in making this move of, well, how is my evidence consistent or not consistent with some true state of the world. The idea of trying to draw conclusions based on a likelihood alone is going to be foreign to a Bayesian. In fact, a Bayesian is not going to be interested in the likelihood ratio per se, or likelihood statistic per se. Instead, they're going to be interested in what we call a posterior belief density. So now, what is a posterior belief density? Let's find out. So as we just discussed, a frequentist is interested in the probability that some estimate or some data set occurred given the state of the world. And that information is contained in the likelihood. In fact, in some ways, it is what the likelihood is. And let me give you an example of what a likelihood might look like. So suppose that we flip a coin n times. And a coin, if it's fair, is supposed to have a half chance of landing on heads and a half chance of landing on tails. But we don't know. We don't know that. We are trying to determine whether that's true or what's true given the evidence that we have in front of us. So a frequentist would say, okay, well, the likelihood that I run n trials and see k heads or successes is given to me by the Bernoulli CDF, which is right here. Sorry, this is a Bernoulli PDF, not the CDF. I misspoke there. And that's just given by theta, which is the probability of a head. So theta is the PR heads. That happens k times. And tails happens n minus k times. That happens at probability 1 minus theta because these are mutually exclusive events. And the probability that all these events happen as a group is just the product of the probabilities as given by typical probability theory. So probability of k heads is PR one head, k times, or to the kth power. And then we have to pre-multiply by this binomial coefficient nk, which is can also be written as n permutations of k. Actually, I'm sorry, it's I made a mistake. It's n choose k. Right, so n choose k implies or tells you what this binomial coefficient means is it's the number of different ways I could choose k things out of a set of n elements. So basically this just says I could see all of the heads for the first k flips, or I could see k minus 1 flips for the first k minus 1 flips, then I could see a tail, then I could see a head after that. There are lots of different orders in which I could see the heads and tails, and the binomial coefficient pre-multiplied here accounts for the fact that there are many possible ways I could have seen this set of events unfold. So you have to pre-multiply by the binomial coefficient in order to get the full probability that I saw this k heads. Frequentists focus on this quantity. So for example, if I was going to conduct a maximum likelihood analysis, what would I do? Well, I'd plug in n and I'd plug in k, and then I'd use some optimization routine to find the theta that made this probability, this likelihood right here, as high as I could possibly get. So I'm going to pick a theta hat that maximizes the likelihood. It's exactly what it sounds like. That's what a maximum likelihood analysis is. The only trouble is that that's not often what researchers are really interested in. Why do I want to know the probability that k heads occurred given some state of the world? What I really want to know is what's the probability that the state of the world is something given the number of heads I see? So how do I figure that out? Well, a frequentist doesn't necessarily know how to proceed because their statistics are built on likelihoods, not probabilities. In fact, one of the very common things that you often end up teaching in an undergraduate statistics class is be careful not to interpret p-values as probabilities about the parameter, because they are not. They're probabilities about the data set's occurrence given a certain true value of the state of the world, given a true value of a parameter. So indeed, frequentists often make a point of saying that this thing that we probably want to know is not actually what a frequentist analysis tells you. In application, we probably want to know, like, for example, what's the probability that the coin is biased towards heads, or maybe the probability that it's biased towards tails. And if either one of those quantities gets too far away from a half, then I'm going to be concerned that there's bias, the coin is biased. Bayesians share this view that this is what we're interested in, and thus they've developed a mathematical framework to tell you what these things are. So what a Bayesian would say is, well, there's some state of the world theta, maybe it's real, maybe it's just a useful theoretical fiction. And what I want to know is I want to establish some beliefs about what theta is. So if theta is a discrete quantity, so that is to say it only takes on integer values, for example, or in other words, it's countable and finite. Well, I guess it wouldn't necessarily have to be finite. Countable, I guess, is the real meaning here, not infinitely divisible. What's the probability that theta is some particular value given the data? Now, for a continuous theta, like a probability, which can vary infinitely between any two values, I can always subdivide. I can always find room between any two probabilities. If you tell me 0.5 and 0.51, I can find a gap between that. No matter which two probabilities you tell me, I can find a gap between, or I can find a value between the two. If it's continuous, then I have to resort to integrals. And you might say, well, what's the probability that theta is in a particular range? And these mathematications are just statements of belief. So what I want to know is, what probability do I assign in my head when I'm making decisions to the idea that theta is a half, or theta is between a half and a quarter? What do I think about that? What probability am I going to assign to that state of the world occurring? Now, I could just make up things, but making things up is not an especially scientific way to proceed. So how do we do that? The answer is Bayes' rule. Bayes' rule gives us a way of translating evidence into beliefs. So that's why it's called Bayesian statistics, because Bayes' rule is at the heart of it. And now we're going to talk about how one would actually do that. So Bayes' rule is the mathematical statement of the relationship between likelihood and our posterior beliefs about a parameter. Now, Bayes' rule doesn't necessarily apply just to beliefs. In fact, it doesn't apply to just beliefs. It's an abstract idea. It comes out of probability theory. And what it says is that the probability that an event A occurs given that another event B has already occurred is equal to the probability that B occurs given that A has already occurred times the probability that A occurs divided by the probability that B occurs. And probably the easiest way to illustrate this is via a Venn diagram. So if you think of there being two events, A and B, here's event A, and here's event B. And the entire world, or the universe of possible events that can occur, is going to be given by this square here. So I have both a MasterCard and a Venn diagram. So this is the universe of possible events, all possible events. Oops. Jeez. Help me out here, pen. So the probability that A occurs, for example, is the ratio of this blue circle enclosed inside the blue circle, this shaded region, well, I'm not shading it, but it would be that shaded region right there, divided by the area of all events. So Bayes' rule says we want to know probability of A given B. So in other words, given that B has already occurred, so given that this red circle is now the world of all events because we know B has occurred. In fact, I should probably state this is not all events, this is really all possible events. Now that B has occurred, we've narrowed that situation down. It's no longer this entire black box, it's only inside of this red circle because we know B has occurred, so that's where all possible events have to be. They have to be inside this B circle. B has occurred. Now we want to know, given that that has happened, what's the probability that A will occur? Well, it's got to be the shaded region right here of the overlap between A and B. It's the part of A, the number of events in which A and B both occur, right? That's this shaded region right here. So if you relate Bayes' rule to this diagram, you'd see, okay, so if I were just doing this as areas, what would I do? Well, if I wanted to know the probability that A occurred given that B had occurred, I would say, well, first of all, what's the universe of events? Well, that's got to be B. B has occurred. So this is going to be some ratio or some number between 0 and 1 because it's the red area divided by the black area. What I'm telling you is we've narrowed down our options from the very beginning. Now the universe is B. The B has occurred. So this is a normalization to say that B has occurred. Now we want to know, okay, what's the probability that A will occur given that B has occurred? Well, that's the same as the probability that B would have occurred given that A had occurred. So in other words, if A had occurred and the blue circle were the universe, that exact same shaded region would be the probability that we're interested in. But remember, we multiply by probability A here because the probability that B occurs, given that A has already occurred, is normalized by the area in the blue circle. Now, in this case, the circles A and B kind of look at the same size, so you wouldn't necessarily need to know, well, why would we need to normalize by probability of A? Well, but that's true, but imagine that instead of A being this size, it was much, much larger. So imagine it was like hugely larger. Now, you can tell that that little shaded region is a smaller proportion of this big circle A than it is of the smaller circle B. So if we're going to take this probability B given A, we've got to basically multiply by how big is A, how big is the universe of events in which A had occurred. In other words, we've got to establish how big this shaded region is relative to the probability that A could have occurred. So we take PRB given A and then multiply by PRA in order to renormalize it to the right area. So you might be able to see visually how PRA given B is related to PRB given A given a Venn diagram. There's also a sort of proof that you can do mathematically if you want to see it in a different way. And I can easily show you how that works as well. So let's start with, so the way this works is you start with the probability that two events A and B both occur. Now definitionally, as a matter of probability, you can say that the probability that A and B both occur is the probability that B occurs given that A has already happened times the probability that A has already happened. There are various ways you can actually relate this back to elementary laws of probability, but this is reasonably intuitive to understand. If two things are going to happen, first we need to know what chance the first one happens, and then given the first one happens, how likely is it that the second one will happen? But we could just as easily have written this in the opposite direction. Well, instead of probability of B given A times probability of A, we could have said, well, what's the probability that A happens given that B has happened, and then what's the probability that B has happened? So these are just sort of basic probability, conditional probability statements, sometimes given definitionally or intuitively, but these are sort of basic axioms of probability. They can be related to even more basic axioms of probability if you like, but we're just going to start from these as definitional. And then I can say, okay, well, if both of these things give me the probability of A given B, then they're equal to each other. And pretty quickly you get to Bayes' rule. Probability of B given A is the probability of A given B times the probability of B divided by the probability of A. This is Bayes' rule. There are straightforward extensions of Bayes' rule to multiple events or continuous parameters, both of which are basically just straightforward ideas that relate to the simple event case. For example, if AI is a part of a bigger set of events A, then the probability that that particular event occurs given that another event B has occurred is just the probability that B occurs given that AI has occurred times the probability that AI occurs divided by the sum of the probabilities that all of these things, that B occurs given that all of these things have occurred. This denominator is still fundamentally the probability that B occurs. What we're doing is saying, well, there's a bunch of different possible things that could have happened. So here's the set of possible things again. Some of these are called A1, some of these are called A2, some of these are called A3, some of these are called A4, and some of these are called A5, okay? And we want to know what's the probability that, say, A1 occurs given that B has occurred. Well, B can span a whole bunch of these different things. There's B right here. And so we have to normalize by the probability that B has occurred, which is built into the function right there. And so what we have to do is say, well, what's the probability that B has occurred given that A1 has occurred, given that A2 has occurred, given that A3 has occurred, given that A4 has occurred, and then given that A5 has occurred, even though there's no overlap in this case. So this is still the same thing as it was before, but we've got multiple different A events we've got to sum over in order to get the total probability of B. That's the only extension here when A, the thing we're interested in, has multiple different possible things that can happen. Continuous parameters are, again, just a fairly simple extension. If I want to know the probability density that theta is a given value, given that something B has happened, I want to know the probability of B given theta times the probability of theta, and then this is the probability of B. In fact, all we're doing here is integrating out theta. We're integrating over the distribution of theta so as to get at the distribution of B, or get at the total probability, rather, of B. In fact, you might recognize this as being somewhat akin to a CDF. It is somewhat akin to a CDF in the sense that we are accumulating the probability that B has occurred given a bunch of different things theta might have occurred. So given that theta is theta 0, theta 1, theta 2, add up all those different probabilities that B has occurred given all those different states of the world, and you get the total probability that B has occurred. So you should definitely, as a part of a Bayesian statistics class, know all of these different variants of Bayes' rule, as the name is quite an accurate description of what you're going to be doing. Bayesian methods involve Bayes' rule. So if you're not familiar with how these things work, get familiar with them very quickly, as they're going to constantly be appealed to in all of the models and methods that we'll eventually use. Now, you may have noticed that there are really three different things that go into a posterior distribution formed by Bayes' rule. So this is what we're interested in. We're interested in what's the state of the world given something. And usually this B thing is that some data set has been observed. Usually B is data. So what we want to know is what's that probability? Bayes' rule tells us what it's supposed to be. There are three things that must go in. The first thing right here you might recognize as the likelihood. This is particularly evident if B is the data set, or B is, for example, a particular estimate that we happen to derive. But usually B stands for the data, and this is going to be the likelihood that the data set occurs given that theta is a particular value. The second thing that goes in is f of theta. Now this is our prior belief about theta before we conduct this analysis or see this particular data. So in other words, we have to start with some beliefs about what the world looks like. Those starting beliefs are going to factor into our eventual judgment given the data, and this is how they factor in. They factor in as a probability distribution that goes straight into the posterior. This is often just called the prior. And then on the bottom here, what we've got is a normalizing constant. And this is there to ensure that the posterior is a proper posterior, which is to say a proper probability distribution. It sums to 1. We need the probability that theta is something given the data to equal 1. If you go back to this Venn diagram, this is the idea that given that we know that something has occurred, we can rule out a bunch of other events, which sort of shrinks our universe down from this big black box down to just this red circle. But we need to, given that red circle is now the universe of possible things that could have occurred, we need all of our probabilities to be relative to that universe. So this normalizing constant just makes sure that everything sums to 1. And the reason why we often are going to end up ignoring this is because no matter what particular value of theta we're examining, that constant is going to be the same because it actually integrates out theta. It's PRB, probability that the data set is what it is. So in fact, oftentimes posteriors are written not as equalities, but using this little ½ symbol, which means proportional to. And the idea here is that our posterior beliefs about the state of the world theta are proportional to the likelihood that a particular data set has occurred given that that is the state of the world, and the prior, what we thought about the possibility that theta was theta before we entered in on this study. So going back to the coin flips example, we already know what the likelihood is. The likelihood is going to be nk, where this is the binomial constant here, theta to the k, 1 minus theta to the n minus k. This is supposed to be a cap n. Okay, that's fine. There are some things we can strip out right away. In fact, this constant right here, this binomial coefficient, can be stripped out because it would be the same for any value of theta. So we can actually ignore this when we go to construct the posterior to some extent. You'll see how this works out later. That's not really going to change what we think about our posterior beliefs. It's just going to be something we need to divide by in order to make the posterior equal to 1. We also have to have some prior beliefs about theta. What did we think theta was before we entered in on this study? There are lots of possibilities that we could write. We could, for example, say, you know what, I think theta is 0.5, meaning I think the coin is probably fair, but there's some chance that because of the wear characteristics of the coin, you know, it's been in a drawer it's all its life or something, rubbing back and forth on just one side, or it's been abused or whatever. I think that there's some chance that theta might be sort of somewhere around a half, but not exactly. So if I was going to plot here on the y-axis, what's my prior belief density about theta? Maybe I have some kind of humped distribution around 0.5. Maybe I'm kind of ignorant about it, and I just say, well, I know it's between 0 and 1 because you can't have more than 100% coin flips come up heads, or less than 0% coin flips come up heads. But other than that, I have no idea. And so I sort of say, okay, well, all values of theta are equal probable as long as they're inside 0, 1. That's another possible prior density that I could construct. I could have all kinds of crazy things. I could say, well, I think it's one of the decimals. So it's, 0.1, 0.2, 0.3, 0.4, 0.5, why, but it's nothing in between. Why I would think that, I have no idea. But one could. But no matter what my prior is, I need to use Bayes' rule to combine this prior belief with the number of flips I observe and the number of heads out of those flips I observe could then push those two things together and construct a posterior belief density about what I think about the coin now that I've seen it flip sometimes. How do I do that? Well, let's look at R and see some ways to do it. In fact, it's actually going to be pretty simple to do this, even for rather complicated prior densities. So here we are in R, and what I've done here is I've constructed a posterior function, and it takes in a theta, an n, and a k, and I've defaulted n and k to be 50 and 20, which is to say I've seen 50 coin flips and 20 of them came up heads. And all it does is it says, okay, well, here's the likelihood function. You notice I have not included the binomial coefficient in here. I've just included the parts that include theta. That's going to actually be perfectly fine. You'll see how that turns out later. I've constructed a prior, and in this case, here's my prior. If theta is less than 0.02, I have some chance of thinking that that's true. Otherwise, I have no chance of thinking that's true. What this prior density says is I think this coin is biased towards tails, and I refuse to believe that it's not. That's what this prior density is telling. That's what it says. No matter what I observe, I think this, prior to my observing this, this experiment, I believed that this coin was biased against heads, biased towards tails, for certain. I think that that's definitely true. And so all I do is multiply the prior and the likelihood together, ignoring the normalizing constant for the moment. Just to check, I have to make sure that my posterior doesn't violate the boundaries where if theta is bigger than 1 or theta is less than 0, I should have no chance of believing that's true because those are theoretically not possible. So I just insert a couple of statements in there to force that to be true. I could have also inserted those in the prior. I could have just said if the absolute value of theta is less than 0.2 and bigger than 0. That would have had the same effect. And then it just returns the likelihood function. So what I do now is I'm going to feed a sequence of thetas from 0 to 0.4 into this posterior function and get some samples. Or get some, I'm sorry, not some samples. I'm going to get some density estimates. Now if I just look at the first few density estimates here, you can see they're very, very, very small. And in fact, they don't sum to 1. Or rather, they don't how should I put this? I should be able to add up integration-wise all of the different slices and have them sum to 1. And in fact, that is not what happens. If I sum posterior density times, let's see, how many things have I got here? I've got like something like 4,000 sequence, so length of theta sequence. I'm getting a number that is not 1, and it actually should be 1. So what I'm going to do is I'm going to correct this normalizing constant right now by just saying, okay, I'm going to take my posterior densities and I'm going to divide by their sum, and then multiply. I actually need to multiply this here by the length of theta dot sequence. And so what I just did is I'm going to force this the series of samples to sum up to 1. So now if I do this post-end plot here, and I say, what's the integral under my density? I should be able to estimate this integral by saying, well, sum up the post-density plot times 1 over whatever the width of the bin is. The width of the bin is the length of theta dot sequence. That should sum to 1, and it does. This is a proper posterior density. If I integrate under it, it sums to 1. So all I did, this is why I can neglect all those constants in the posterior density. I can fix that all once I've constructed them, and I don't even really have to know how to fix them. All I need to know is a posterior should integrate to 1, so I just force it to integrate to 1. Now I'm going to make my thing square here, and if I plot this out, well, you can see there's coming out as lines. Maybe I want to change this to, or it's coming out as dots. Maybe I want to change this to be a line plot to make it look nicer. If I plot this out, type equals L. There's my posterior density. Now, what is this posterior density telling me? It's telling me the following. Well, there's a really good chance that the theta sequence is, the theta is 0.2. There's a much less probability that it's less than 0.2, almost no chance that it's less than, say, 0.15. But there's also no chance that the theta is bigger than 0.2. Why is there no chance that theta is bigger than 0.2? In fact, there should be a really good chance because 20 out of 50 came up heads. 20 out of 50 flips came up heads, and 20 out of 50 is 0.4. So I would think that theta should be at least 0.4. How come my posterior has no probability assigned to 0.4? Well, the answer is if there's no weight on that value in the prior, there can be, by definition, no weight on that value in the posterior. If I say, prior to evidence, I do not believe under any circumstances that theta could be 0.3, 0.4, 0.5, no amount of evidence is going to change my opinion. I have to at least allow some chance in advance of the study that this is true in order for the study to update my beliefs in that direction. And this in the Jackman book is called Cromwell's rule. If there's no prior density assigned to a particular belief or value, a parameter value, no amount of data is going to make it have positive probability. I'm just not going to believe it if it's not in the prior. So when you construct priors, you should think very carefully about whether you assign zero probability to some event occurring, because once you do that, no amount of data can, by construction, change your mind. And that's not a very good position for a scientist to be in, saying, I will never change my mind no matter what data I happen to see. So this is kind of a crappy prior. Maybe I could do better. This time I'm just going to say, well, my prior probability is, I'm just going to set it to a constant 1 for everything. Now, you'll notice that prior is not proper. If I integrated a prior density that set 1 as a value no matter where I was, anywhere on the function, I would integrate, if I integrated from theta equals 0 to 1, I would, actually in this case, I would get a prior probability. Actually, yeah, it would be fine because you actually would be a proper prior in this particular case. But it wouldn't necessarily. I could actually set this to 5 and it would still be. Now, that would integrate to 5, and that's obviously not a proper prior, but it's not going to matter because I'll just come down here and divide by the sum of the posterior density, and then actually, hold on. Multiply by the length of theta sequence divided by the sum of the posterior density, and I can sort of fix that all on the back end. There's gonna be no problem, even despite the fact that my prior is improper. I'm just gonna normalize it and everything's gonna be fine. The only thing that really matters is relative to other values, the prior is the same. In other words, I've made it flat. This is a so-called flat prior. I've said every value of theta between 0 and 1 is equally likely. So going back to the notes, I've drawn this line, this flat blue line, and said I'm completely ignorant about what theta is going to be before having conducted this study. So if I rerun all this, and actually I can obviously do better if I do type equals line, plot this out. Here's my posterior density for theta after having conducted the study. And you can see it's centered on 0.4, which is what I would have gotten if I just divided the number of successes or heads by the total number of trials, 50. Now there is uncertainty around this estimate. I could, this set of trials could be partially the product of luck. I could have just as easily seen 22 heads or 28 heads, maybe some chance, or 19 heads. And so I'm not sure exactly what the probability of theta is, because I'm not sure exactly if this data can't tell me that much information in essence. But it's centered on 0.4, which makes sense. Now, suppose I want to actually have an informative prior density. I want to say I know something about whether this coin is biased or not. In this case, my prior is going to be a normal density centered on 0.3 and with a 0.1 standard deviation. So I'm going to just run this through and plot out what my posterior looks like. There it is. And you can see it's shifted toward 0.3. What this is telling me is my prior is actually pulling the data toward itself and sort of drawing my conclusions closer to what I thought before. But the data is having an effect, and you can see that if I plot the prior density in here, it used to be centered on 0.3 with 0.1 standard deviation. The data has shifted me toward 0.4, but not completely toward 0.4. Posteriors are in some sense, a weighted average or a combination of what I thought before the experiment or this particular data set was realized, and the data contained in that data set. So, literally, as it's written in the notes in this prior thing, I'm sorry, right here. The posterior beliefs about a parameter are proportional to the likelihood and the prior. They're a combination of the likelihood and the prior together. And you can see that in this little toy example. Information that is contained in the prior is included in my eventual inference. That makes perfect sense. I don't immediately change my mind completely given just one new experiment. I look at that experiment and I say, well, what can I learn about that experiment? What can I learn about the world given what I already knew plus this new experiment? That makes perfect sense. It does raise the question of where do priors come from and how do they influence our analysis, which is a perfectly reasonable question to ask. But it would be extremely irrational to say, I'm going to forget about everything I know on the basis of seeing a little bit of new data today. Bayes' rule tells us, in fact, how to optimally combine what we knew before with what we know now, and so it makes sense that the thing we believe now is some sort of combination of those two things. So from our analysis of how the prior and the likelihood combine to create a posterior density, you might immediately be thinking, well, gee, our conclusions seem to be related to what we believed prior to this analysis being conducted, which, as we discussed, makes perfect sense. But it also leads us to think, well, how much are our priors really informing what we believe, and can we get a sense of how our current beliefs, our posterior beliefs, are influenced by those priors? And the answer is yes, we can. We can just redo the same analysis with multiple different priors to get a sense of how sensitive our conclusions are to those priors. And so I've just got this code here that I created for the example of coin flipping, and you can see the prior here is a normal density centered on theta with mean 0.3 and standard deviation 0.1. This is not an especially great prior because it allows there to be prior weight on thetas outside of this 0-1 interval, which is kind of stupid. So we might think about, okay, maybe we can set the prior to something that limits it to 0-1 if we wanted to get serious about this, which is, yeah, one should do that. But for the time being, say, well, suppose that we were more convinced in advance. Suppose our standard deviation was tighter on the mean being 0.3. In other words, we were just more convinced that, hey, this is a biased coin. I know this is a biased coin, and it gives too few heads. Well, if I rerun my analysis, you can see how the prior has changed, and how the posterior is now sort of tighter and has moved toward 0.3. And if I make this even tighter yet, oh, actually, I need to change this as well. So hold on, let me go back. 0.05. Here we go. Right. So I've made the prior tighter around 0.3, and my posterior is reflecting that increased prior certainty by becoming spikier, sort of more concentrated, and also shifting closer to 0.3. If I get less certain, so if I set this to, say, 0.5, so I'm going to set both of these to 0.5, now you can see my prior is much more spread out. In fact, it does cover areas of theta that are not inside the interval, and so in that sense, it's not the best choice for a prior, but nevertheless, you can see I've got a distribution over 0.0 to 0.8 there. And my posterior has spread out accordingly and is closer to 0.4. It's centered on 0.4, which, in other words, it's closer to what we saw in the flat prior, where I was completely unconvinced. I had no conclusions about what the posterior or what the value of theta was, whether the coin was biased prior to my experiment. And what I can do is just try different values of the prior and see how my conclusions change and get a sense of, now, I don't want to go fishing for what's the right prior to use to get the answer I want. That's not what I'm suggesting. What I'm suggesting is, how robust are my conclusions to different prior beliefs? How convincing is this evidence to people with different sorts of priors? And in general, what you can tell is, the more certain a person is before the experiment, the less they learn from the experiment, which again makes perfect sense. So you can conduct a sensitivity analysis and literally show, here's how people with different prior beliefs would interpret this evidence in different ways and come to posterior beliefs. And you can communicate that fact to your readers and give them a sense of how different sorts of people might interpret this evidence in different sorts of ways. In that sense, you can turn a potential weakness of Bayesian statistics, which is to say its dependence on prior beliefs, into its strength. You're able to quantify and communicate the fact that people with different entering beliefs will interpret evidence in different ways. So I suggest that when you conduct a Bayesian analysis, you think about what your prior beliefs are prior to the experiment, but then post hoc you also conduct a sensitivity analysis to see, well, how much do my conclusions really change depending on what I believed before the experiment was conducted. That's a perfectly reasonable thing to do. That's not to say that priors come from nowhere. In fact, priors can come from sources, particularly from the literature. Priors can come. Separate that from my underlining there. So chances are, even if this is the very first investigation into a particular area that's ever been conducted, which is unlikely but possible, that doesn't mean there aren't ideas about the relationship that you're investigating that are already out there. And so priors aren't just, we can sort of play around with them to figure out sort of how sensitive our conclusions are to what they are, but we can also use the existing literature, both theoretical and empirical, to inform what our priors ought to be before we come into an analysis. So in conclusion, or at least in conclusion to this particular part, priors do change what we believe posterior, in the posterior after a particular investigation is conducted or an experiment is run. We can conduct sensitivity analysis to get a sense of how much those posteriors are affected by our priors, and we can also make an effort to see that our priors are informed by previous research, either directly into literally parameter estimates from earlier data sets that have been conducted in a similar setting, or even from vaguer theoretical notions that come out of the extant literature on a topic. Now, as a set of computational or statistical tools, one of the strengths of Bayesian analysis is how flexible it is. We can specify likelihoods and priors that are very, very complicated, and the Jackman book has some examples of this. We can write down priors where our belief about some parameter theta is bimodal or multimodal. We can have lots of different modes here. It can be perfectly uninformative or flat, all sorts of different things. And in addition, our likelihood functions can be quite involved as well. We're not necessarily bound to the strictures of the GLM framework that we are, as we often are as frequentists, because as it's going to turn out, we have ways of computationally estimating these distributions even when we can't write them down analytically, or we have a hard time writing them down analytically. So this is one of the main strengths of Bayesian analysis. We have ways of combining prior and likelihood information to form a posterior, even when the prior and likelihood are very complicated. But it turns out that sometimes the prior and likelihood are simple, And if they're simple enough, there are things we can do to write down a posterior that's analytically closed, which makes it very easy to show, to depict, and to do all sorts of post-estimation analysis with, because we can work with it directly in R. There are some examples of how this works. I just want to show you a couple of simple ones. One very simple and another that's less simple but much more practical. So we were just working with a binomial distribution in the context of a problem with coin flips. And the binomial likelihood, as you saw, looks like this. The binomial likelihood, as it turns out, has a prior distribution with which it is conjugate. What do we mean by conjugate? A conjugate density is one in which the prior and a conjugate prior, I should say, is a prior that fits together with a likelihood in such a way that the posterior that comes out is, there are varying definitions here, but one of them is in the same family of densities as the likelihood. One of them is just that it's analytically closed. If we can find a prior for which, when combined with a likelihood, it forms an analytically closed posterior, that is in some sense conjugate. This leads us to ask, what are conjugate prior densities for various likelihoods? And in the case of the binomial likelihood, which we've got written down here, one particular conjugate density is the beta distribution. So here's the beta distribution. It's got this leading constant here, which includes the gamma function, which is kind of a complicated function. But as it turns out, that's a normalizing constant that we don't necessarily have to account for the same reason that we don't necessarily have to account for the binomial coefficient up front in front of this likelihood when we compute posteriors. So really, the most important bit here when we combine the prior and the likelihood to form a posterior right here, and actually, this should be proportional to as well. Let me get in there and fix that. Whoops. There we go. We can, as we did before, neglect this binomial coefficient and this leading coefficient on the beta prior and focus in on just this bit right here. And you can see that what's happened is the alpha and beta parameters of the beta distribution have, by the laws of exponents, just substituted directly into the binomial likelihood to form a quasi-binomial posterior density. In fact, alpha and beta in the beta distribution literally translate into numbers of trials that were observed to be successes and failures in some sort of prior experimental or other kind of observational context. And this is perhaps easiest to see in R. So I'm going to just show you, first of all, what the beta density, the beta prior density looks like. And I've got a sequence of thetas from 0 to 1. And the beta density is given by d beta. It's integrated directly into R's set of functions. And what I'm going to do is start off by showing you a beta density with alpha equals 30 and beta equals 30. So alpha and beta, if you look at the help function for d beta, are given by shape 1 and shape 2 parameters. That's what alpha and beta correspond to in this case. So I'm setting alpha and beta here, but they're called shape 1 and shape 2 in R's language. So if I have 30 successes and 30 failures, the beta distribution, the beta prior, is centered on 0.5, which is exactly what we would expect, half successes and half failures, and has some kind of spread. Now, if I reduce those successes and failures to 3 and 3, I'm still centered on 0.05, but a lot less certain about that, which makes sense because if I've only observed 6 total trials, I don't really have that very much information, and so I'm less certain. So you can see, as we alluded to before, that in certain cases, prior probability densities can actually come from previous runs of an experiment or previous papers that are written in a particular area. And in this case, in the binomial likelihood case, That's literally true for the conjugate beta density for a binomial likelihood. We can literally put in the number of successes and failures that we've observed in the past and get a prior density that's appropriate. Now, that's not the only way to run the railroad. We may not have seen any prior experiments, and so we may be simply figuring out a beta density that roughly corresponds to our beliefs, and we can just play around with successes and failures and look at visual depictions of that to get a sense of what prior we want to specify. So you can see that reducing the number of successes to 25 shifts the prior density over a bit to the left to indicate a lower probability of successes. And we can play with this as many times as we need to in order to get the prior that we would like. So if I now use this prior density, here's the prior density right here. You can see I've added two parameters, alpha and beta. This is the truncated or sort of appropriately corrected, or not corrected, but appropriately snipped form of the beta density that excludes that leading coefficient with the gammas. And I put an alpha of 10 and beta of 30, which tells me that in the past I've seen 10 successes and 30 failures out of a total of 40 runs. I don't necessarily have to have literally observed those successes and failures. All that's required is my prior density needs to look like this. And in other words, this is expressing a good deal of certainty that the coin is biased away from heads prior to having observed this particular pattern of coin flips. So if I run my model here, you can see the solid line is the wait just a second here. I see what happened. I have the wrong prior dialed in. I need 10 and 30. Let's try that again. There we go. So the dotted line is the prior, and the solid line is the posterior. So if I set the prior according to this beta density, what I get here is, okay, look, I used to think that it was a coin that had 0.25, 0.3 chance of turning up heads. Having seen this experiment, now I believe it's closer to 0.3 with tighter uncertainty. I'm more certain of that, but I've still got some uncertainty. That's what happens here, and I can play with different priors to see how that changes my posterior, having seen this experiment, if I wish. The one thing that's really nice about this is, first of all, the conjugate prior allows me to express that prior information in a very sort of understandable format. But secondly, it's very easy to figure out analytically how to dial around the prior. I mean, I have a closed form analytic expression for the prior that translates actually into a closed form analytic expression for the posterior if I wish to take advantage of it. I don't have to worry about the leading coefficient so much because just like before, I can force these densities to be proper. I can divide by the right constant and force them to be to have integral equal to 1 if I need to do that, which you can see I did it in this case. It's no big deal at all. So in frequentist hypothesis testing, we have p-values and likelihood ratios and things like that. Bayesian hypothesis testing is in some ways much more straightforward. What we're going to do to test hypothesis in a Bayesian framework is first establish some kind of criterion for drawing conclusions about a quantity of interest. And in particular, we're going to focus on typically the probability that theta is in some region, in this case cap theta, given the data. So there are lots of different ways this can link to hypothesis testing as you might understand it as a theoretical exercise. For example, we might say, well, our theory tells us that some slope, for example, some dy dx should be greater than 0. It should be positive. And so what we might assess in a Bayesian analysis is, well, what's the probability that some measure of the slope, like a beta coefficient in a regression, we'll say beta here to keep the notation consistent, what's the probability that beta is 0 given the data that we've observed? This is a posterior. What's my posterior belief that the slope is positive given the data? So theory leads us to look at certain quantities of importance, and Bayesian statistics allows us to directly assess those quantities of importance, which, as you recall, we couldn't do with frequentist statistics. Theory tells us that a slope is positive, and when we do a frequentist hypothesis test, what we end up asking is something like, is the data consistent with the idea that beta is equal to 0? That's not really what we want, though. What we want is, what's the probability after having seen the data? What should I believe about the probability that it's positive? So in that sense, Bayesian hypothesis testing is much more direct. It's much easier to explain, particularly to a non-technician. You can literally say, hey, after examining this evidence, I thought there was a 30% chance that the slope was positive. That's terrible. It's a 70% chance that it's not positive, so theory's not so good. Or there's a 90% chance, 95% chance, an 80% chance. These are things that are easily to explain to outsiders, make a lot of sense, make a lot more sense than saying, if there's absolutely no relationship, if beta is exactly equal to 0, a data set or a parameter of this size would have occurred 5% of the time or less. It's much more that's much more confusing to explain. Nevertheless, Bayesian hypothesis testing does typically import some frequentist ideas. For example, it's very common to say, well, I'm interested in whether beta is bigger than 0 because that's what theory tells me it should be. So what I'll do is I'll compute the area under the posterior density from negative infinity to 0, and maybe I'll draw some conclusion on that based on the size of that density. So here we go. We've got a parameter we're interested in, like a slope, a beta here, and we've got a posterior density over beta given the data. And my theory tells me, hey, look, this should be positive. So area to the left of that is, in other words, it countermands my hypothesis. And evidence to the right of that is in favor of my hypothesis. So what I might say is, well, I'm going to buy this conclusion if my belief that I'm wrong is some quantity. And, one common quantity is the good old alpha of 0.05. If there's a 5% chance that this conclusion is inconsistent, I'm sorry. If my beliefs are more than 5% inconsistent with this conclusion, I'm not going to buy it. So I could do it. I could do something like that. And that does sort of borrow some moves that are sort of evocative of frequentist statistics. In general, this sort of idea revolves around constructing what are called credible regions of the posterior density. A credible region is just any integral over the parameter of interest, like beta, that covers 1 over alpha proportion of the density. So, for example, going back to here, I've got a credible interval here that covers 95% of the density. This is 0.95 right here. So the integral from 0 to infinity is a 95% credible region. Now you'll notice that's not the only 95% credible region. I could have just as easily done this. I could have said, well, this and this right here, this is say 0.025 and this is 0.025. So between here and here, I've also got 0.95% of the posterior density. That's also a 95% credible region. So credible regions are actually not unique. A credible region is just any region that basically has 1 minus alpha percent of the density underneath of it. But there are credible regions that are considered optimal. And generally speaking, those are ones that cover the portions of the density that are the highest. So let me give you an example of that. Suppose we've got a posterior density here. Here's f of theta. Here's theta. And suppose we've got some really weird posterior. So like something that has a binomial density. Okay. And I want to construct like a 90% credible interval. Now, there are lots of ways I could do that. I could maybe get 90% coverage by drawing right here and saying, okay, well, 90% of the density is underneath here. That's perfectly fine, whatever. But what we want to do to make this optimal is to say, well, I want to actually make sure that the credible interval that I identify is the interval that covers the areas under the density that are highest probability. So, for example, it's comparatively quite likely that theta is theta 0 or theta 1 compared to out here with theta 2. So my credible interval should cover theta 0 and theta 1 long before it covers theta 2. So in essence, what I'm going to do is I'm going to start at the maximum of the density here, and I'm going to basically move down, move down, move down, and at every point I'm going to say, okay, what's the integral of all the areas whose density is bigger than this particular point? So for example, for this line, I'd be calculating the density under here. But if I went up higher, so if I went, I'm going to use gray. So if I use this line right here, I would identify these points, which are a little bit closer in, and I would take the integral under those areas. So I keep sliding this threshold down until the integral under the area equals my target. So if, for example, if I'm constructing a 90% credible interval, what I'm going to do is lower this threshold until my integral equals 0.9. And then I'm going to stop. And I'm going to say, there's my credible interval. So these are in some sense optimal because they identify the regions of theta, my parameter or quantity of interest, that are most likely under the posterior density. So it provides some sort of regularity to the idea. And you're going to construct credible intervals in your homework. There are lots of different ways we could think about constructing credible intervals. If the distributions, if our posterior distributions are nicely symmetrical, for example, if they're normal or t densities like we had in our Bayesian regression example, then maybe we can just say, okay, we set t densities of 1.96 and negative 1.96, and we just keep sliding it out until we get a whatever. That might be nice. That might work as long as the distributions are symmetrical. But if they're asymmetrical, or if, like in this case, if they are bimodal or in some way kind of weird, we might need to think about a more computational way of doing this. And so in your homework, I'm going to encourage you to think about some computational ways of constructing credible intervals that don't rely on the symmetry of the posterior distribution, because especially when we get further into our class, many of our posterior distributions will be highly irregular, not symmetric, or even actually they may not be analytically solvable. So I want to get you thinking about constructing credible intervals in a computational kind of way. So I'm going to end up today's discussion by returning to issues of model comparison, which we dealt with last week. And the Bayesian perspective on inference leads us to consider a model comparison statistic in addition to the ones that we considered last week. It's called the Bayes factor. The idea behind the Bayes factor is, look, I want to know whether the probability that model 0 is good, is the right model, or at least a more useful model. I want to know whether that's bigger than the probability that some other model is good for some data set. And if so, I accept model 0, and if not, I accept model 1. And maybe I don't just look at exactly which one's a little better or worse. What I actually want to say is, well, maybe I favor one of them is simpler, more parsimonious, it's accepted in literature or whatever, and so I really need exceptional evidence in order to conclude that a model is better. And what this leads us to is a statement of the Bayes factor. A Bayes factor says, okay, I've got two models, 1 and 0, and I want to know the ratio of their probabilities given y times the ratio, or the inverse ratio, I should say, of their priors. Another way of writing this, which might make it a little simpler, is if I go over here and say PR M1 given y divided by PR M0 given y divided by PR M1 divided by PR M0. These here, where are we? Oh, there we go. Let me get a blue pen. These here are the posterior density ratios for a particular model. And these are the prior density ratios, where are we right here? And the idea is it the case that after having looked at evidence, the ratio between these two models got more favorable toward Model 1 or less favorable toward Model 1? So in other words, I had some sort of idea about how likely Model 1 and Model 0 were before I got started. Is it the case that that data led me more toward that conclusion or less toward that conclusion? That's what the Bayes factor is sort of telling me. And it turns out that ratio is just the ratio of likelihoods of y given the model, which is a little bit surprising, but not too hard to demonstrate. It's actually fairly easy to illustrate. So the probability that we see a particular data set given a model is, by Bayes' rule, given equal to the probability that the model is true given y times the probability that the model is true divided by the overall probability, I'm sorry, it's supposed to be y, probability of the data set occurring, divided by the probability that the model is true. Okay, that's fine. What we want, and we could easily write a similar statement for model 0. M0, sorry, given y times PR y divided by PR M0. Okay. What we want is PR M1 given y divided by PR M0 given y. Okay. Well, in that case, let's rewrite things a little bit. Where is my cursor here? There it is. So I can use Bayes' rule by the same way here. I can say this is going to be PRY given M1 times PR M1 divided by PRY over PRY, given M0 times PR M0 divided by PRY. Well, if I go here, these are going to cancel, and what I'm left with is the Bayes factor. It's the ratio of likelihoods times the inverse ratio of priors. So if I just finish this up here, you can see that this is going to be equal to PRY given M1 over PRY given M0 times PR M1 over PR M0. So, and that's exactly what we started off with right up here. Oh, and I'm sorry. One more step. We need to take this here and then move it over to the other side. So if you move that over to the other side, you get PRY given M1 divided by PRY given M0 equals PM given Y, M1 given Y, divided by PR M0 given Y times PR M0 divided by PR M1. And that is what we have right here. So PR Y given M1 divided by PR Y given M0 is equal to this Bayes factor ratio that we're interested in. So what this tells us is, in order to decide whether data lead us to conclude that one model is better than one another, or at least allows us to update our beliefs in favor of M1, favors M1, all we need to do is calculate the ratio of their likelihoods. That's a simple thing to do, and in fact in R you can see I've already done it here with a minimum of fuss. One thing that is worth mentioning is that for computational reasons, log likelihoods are often used, and so the Bayes factor is given by PRY given M1 divided by PRY given M0, but these likelihoods are often log likelihoods, so in other words we've got logarithms going on, and if we were to take the log of this whole thing by the laws of logarithms, we'd have log of PRY y given m1 minus log of PR y given m0, because ln A over B is ln A minus ln B. So if we start with log likelihoods, what we really need to do is subtract them and then take the exponential to recover the Bayes factor. So that's what we've done here. I've made a fake data set. Let me actually, let's see, Control L, let's get rid of this. What I've done here is I've created a fake data set with x is a function of, y is a function of x is just, y is just half plus 2x plus a normally distributed error. And I've got an irrelevant variable here, z. I'm going to run 3 models, one with y modeled just a constant, one with it modeled using x, and one with it modeled using x and z. So if I did a summary of model 1, you'd get just an intercept. And if I did a summary of model 2, you'd get an intercept and a slope on x, and you can see it's close to 2 as it should be. And if I did a summary of model 3, you'd get x and z coefficients, and you can see the z has a tiny coefficient. It's highly statistically insignificant. So I can compute Bayes factors here, and the first Bayes factor I want to compute is model 2 better than model 1. And so I compute this exponential of the difference in their log likelihoods, and what you can see is that the number is huge. Now, generally speaking, any number bigger than 1 is evidence in favor of model 2 in this case. Any number smaller than 1 is evidence that model 1 is better. And the bigger the number, the more convincing the evidence. And I'm looking at Jackman right here. And Jackman, referring to Jeffrey, says that a number between 1 and 3 is barely worth mentioning. A number from 3 to 12 is positive. A number from 12 to 150 is strong. And a number bigger than 150 is very strong. What is this? Something like 49 million? Yeah, 49 million. I'd say that's pretty strong evidence in favor of model 2. But if you repeat the same thing for model 3, we do get a Bayes factor bigger than 1, but barely. What this is telling us is that, yes, model 3 is better at explaining y. It's a better model of y, but barely worth mentioning. Not really that great. This is sort of comes to the idea back to what we talked about R squared. Adding junk variables in does improve R squared in sample. It also improves your Bayes factor in many cases, and in this case that's true. But not enough that we would actually consider really thinking model 3 was much better than model 2. Yes, it's a little better, but not really so much. And again, relying on this Jackman guideline that comes from Jeffrey's 1961, really we wouldn't start to think about considering a model better until this Bayes factor was at least 3, 4, 5. So in this case, we reject model 3 as being slightly better, but not really so much better that we should care about it. Okay, so there's your crash introduction to Bayesian inference. Now these ideas, if you didn't get them the first time, that's not entirely surprising. You can of course watch the video again. But every week we're going to be hitting on these ideas over and over as we develop more complicated models and computational ways of getting at some of these concepts. So for example, one thing you may have noticed is that even the binomial case, but especially the regression case, the form of the posterior is very, very complicated. That's true, and it makes it hard for us to express that posterior in analytically closed forms. But next week we're going to start to talk about computational techniques that don't require us to express the posterior in closed forms. All we need to do is be able to write down a prior and a posterior, and write down a prior and a likelihood, and we can immediately jump to computationally sampling out of a posterior without knowing how to write it down. This week, when we're focused on how to write it down, you get to some pretty complicated situations, and it can be sort of complicated to understand, wait, what's exactly going on here? This is actually ironic. Introducing the computational tools that we're going to work with next week is actually going to, even though the technology is going to become more complicated, the ideas behind Bayesian inference are hopefully become easier to understand because there'll be less mathematics between you and the ideas that you're expressing. That's my hope anyway. Until then, good luck, and I will see you next week.